So let's talk about ionic compounds. There's lots of ionic compounds. They occur in the Earth's crust. They're in the food that you eat. It's okay, you're eating chemicals. All food is chemicals. Even certified organic food is chemicals. Because all matter is a chemical, right? It's all made up of atoms, right? Now, some are good for you and some are not good for you. But some of them, it just depends on the amount. You can kill yourself by drinking too much water. But you can also kill yourself by not drinking enough water, right? So there's balance involved. Here's some examples. Morton light salt is a mixture of two ionic compounds, sodium chloride and potassium chloride. Tums that you might take if you've got heartburn, that's made of calcium carbonate. Another form of calcium carbonate is called calcite, and it forms these beautiful crystals. You might find those on the inside of a geode or something. And here's another ionic compound, and this has this big, long, complicated formula. We need to learn how to write formulas for ionic compounds. So first we write the symbol for the metal cation, and we need to compare charges. So we need the charge on the ion, and then we write the symbol for the nonmetal with its charge. What we're going to do is we're going to figure out how many of each ion based on the charges, because we have to have overall a neutral substance. So we have to check when we're done that the sum of the charges equals the sum of the charges, the sum of the positive charges equals the sum of the negative charges. Let's make up an example here. So name a metal. Potassium? Okay, so what charge does a potassium ion have? +1. Because it's in group 1. Name a nonmetal. Nitrogen. Okay, so nitrogen forms an anion. What's the charge going to be? 3-. So that's the first step, the symbols with their charges. We need to adjust the subscripts on each of these to balance the overall charge. If we had one potassium and one nitrogen, the charges would add up to -2. They need to add up to 0. Another way is, here we have +1 and here we have -3. I need these numbers to be equal. How can I get them to be equal? I could add 2 more potassiums. So now the total positive is +3 and the total minus is -3. That's what we need. You can't change the charges. Sometimes that would make things easier, but you can't do that. So then we look at this and we say, well, we have 3 potassiums. So that's K3, and I have 1 nitrogen, so I'm going to write the letter N. I'm not going to write a 1 because I'm a chemist and I don't like to write the number 1. If it was more than 1, I'd write a number. If it was 0, I wouldn't write it at all. Right? Another way to do this is a method called crisscross, which students tend to like. So let's just get rid of this. So crisscross, you look at the charges. So this is a 1 and this is a 3. And you say, okay, those are not the same. I can do crisscross. So I'm going to take this unwritten 1. It's going to be the subscript for the nitrogen, for the other one. And I'm going to take the 3, and that's going to be the subscript for the potassium. And so I get K3N1. The 1 wasn't written here, and it's not written here either. Yes?
That doesn't work when you have something that has a 2 and a 2.
You can get into trouble doing crisscross. I'll show you. So what if we had SN 4+ and O 2-? The first thing you have to ask yourself is, are the numbers different? If the numbers are the same, you just push them together. You need one of each. Don't make things harder. Here the numbers are not the same. We have 4 and 2. So if we do crisscross, we end up with SN2O4. Well, overall the charge will be neutral, but is that the lowest ratio? No, it's not. It's SnO2. That is the formula for that compound. Because an ionic compound, we're looking at the lowest ratio, basically an empirical formula. So the crisscross method will work most of the time. You just need to be careful. After you crisscross, make sure that you can't simplify the ratio, and then you should be okay. Any questions? How about magnesium and nitrogen? Well, let's do that. What about magnesium and nitrogen? So magnesium is 2+, right? And nitrogen is 3-. So what about that? Well, we look at +2 and -3, and we said they're not the same. We could do crisscross, and we'll get Mg3 and 2. And 3 to 2, we can't reduce that. So that's one way to do it. A more algebra math way that some of you are really good at, you could look at that and you could immediately see that the least common multiple is 6, and you could just write this down. So I don't need to talk to those people anymore. But then a good proportion of you are not going to get that, and that's okay. So let's think about how this thing works. So I like this method. So I'm just going to, keep a tally down here of how many positives and how many negatives. And I see that I don't have enough positives. So I'll add another of the positive ions, and then I have to adjust the total. So now that's +4. And you're like, okay, well, now it's unbalanced the other way. I need to add a -1. This is where you're tempted to change the charges, but you can't. You can't change the charges. So now I've got -6. Like, great, we're going in circles. I'll just keep going. Let's add another magnesium. And that brings us, that wasn't the eraser, that brings us to +6, and we're like, phew, it finally worked out. 3 magnesiums for every 2 nitrogens. Okay? Any questions? Does that make sense? So, ionic compounds always have positive ion, negative ion. The first element is always the positive one, and the second ion is always let's start that over. The first element is always the positive ion, and I can't say it. The negative ion always comes second. There we go. The first element is usually a metal, and sometimes students, write it backwards, and they're like, why isn't that okay? Well, it goes against convention. So let's pretend you're sending out some formal wedding invitations. Are you going to write Mr. and Mrs. or Mrs. and Mr.? Mr. and Mrs., right? Of course. Why? Because that's the way we always do it. It's always Mr. and Mrs. Did you ever think about that? It doesn't mean that the man is superior. It's just convention. By convention, we always write the positive ion first and then the negative ion. That's another reason to think of the metals as masculine and the nonmetals as feminine. It's the guy's name first and then the girl's name. Not because one's better than another, but just because we decided to do it that way. It's consistent, and so things always look the same, and it makes things easier overall. The one exception to the first element being a metal that you really need to know is ammonium. Ammonium is a cation. It's positively charged. There's no metal in it. It's okay. It's a positive ion. So we just need to remember that one. So we always have the sum of the positive ions, their charges, has to equal the sum of the negative charges. And we're looking for the smallest whole number ratio. So this kind of restates some of the things we already talked about. Examples. Write the formula for the ionic compound that forms between potassium and sulfur. First thing is to write the element symbol and the charge that the ion has. So potassium is K. We kind of used this one in the previous example. It's in group 1A, so it's got a +1 charge. Sulfur is S. What's the charge on a sulfur ion? 2 minus. So there's 3 methods to figure this out. You can do crisscross, you can just look at it, or you can draw ions and sum up their charges. What's the formula going to be? K2S. If we do the crisscross thing, we see this unwritten 1 becomes the subscript for the sulfur, and the 2 becomes the sulfur for the potassium. Overall, an ionic compound is neutral. Notice that when I write the formula for the compound, I do not include the charges. That would make things very cluttered and messy looking, and so we never ever do that. How about aluminum and nitrogen? Just ALN. So aluminum is in group 3A, so it's got a 3+ charge. It's a metal. Metals always have positive charges. The nitrogen, different ways to remember that one. You can take the group number 5 minus 8 gives you -3, or you can count backwards from the noble gases, 0, -1, -2, -3. Here, we don't want to crisscross these, because 3 and 3 are the same. And if we just, I imagine just pushing these 2 guys together. And we don't need to do anything else. And it's just ALN. Any questions? Naming compounds, starting with the ionic compounds. Some compounds have common names, like table salt. That's the common name for sodium chloride. But all chemicals also have a systematic name, a set of rules so that we can all arrive at the same name for a given compound. So the first thing we have to do when we're naming compounds is to identify what type of compound we're dealing with. Because there's one set of rules for ionic compounds, and there's another set for molecular compounds, and there's another set of rules for acids. And then there's another for organic compounds. But we're not going to do those much at all. So how do we identify? We kind of already went over this. Ionic compounds are usually composed of metals and nonmetals. So looking at these 4 examples, they all start with a metal. So you look at the compound's formula and you look at the first element and you ask yourself, is that a metal? If the answer is yes, it's an ionic compound. Let me give you a tricky one. What about NH4Cl? You look at the first element, nitrogen. Oh, that's not a metal? Oh, but this is ammonium ion, and so we need to be able to recognize that as that one weird cation that's not a metal. Lots of chemistry textbooks like to divide up ionic compounds into 2 groups based on which type of metal. And so I'll go over this, but I think it's a little silly. There are the metals that only form one kind of ion, and we've talked about those, the ones in groups 1A, 2A, and 3A. The transition metals and the other main group metals can form more than one ion. And so we have to treat them a little bit differently. So that's what they're talking about, the first type and the second type. So the first type, these are the, didn't mean to do that. The first type, these are basically going to be groups 1A, 2A, and 3A. Plus 2, zinc and silver. We'll talk about those in a minute. And this is all the others. So that's the division. Metals that form one cation. So here we have the group 1A metals and the group 2A metals, and here's aluminum from group 3A. And then we've got just a couple of extra guys down here. Zinc and silver are the important ones to remember. Scandium only forms one ion, but we rarely see scandium, so I don't see any point in remembering that one. When we name these ions, the ion name is the same as the element name. And so Li plus is just a lithium ion. And Be2 plus is beryllium ion. We don't have to do anything special. So those guys are easy. The others, anything that wasn't on that list, these can form more than one ion. And so we can't just use the element name for the ion name. Chromium forms two different ions, +2 and +3. And you're not going to get this information, obviously, from the periodic table like we do with the +1, +2, +3, the groups 1A, 2A, and 3A. These guys are squirrely. They're just unpredictable. So when we name the ion, we have to tell each other what the charge is. So Cr2 plus is chromium 2, and Cr3 plus is chromium 3. We use Roman numerals in parentheses after the name to tell us what the charge is. So here's iron. Iron 2 plus is iron 2, and Fe3 plus is iron 3. The Roman numeral tells us the charge on the ion. There's an older system, and I just want you to know that it exists. We're not going to use it. They used to use suffixes us and ik to indicate the relative charges, but you still had to remember which one, was it 2 and 3 or was it 3 and 4? And they also used the Latin names of the elements, and so it was ferrous ion and ferric ion. I can't remember these myself, and so I'm not going to make you remember those. But just know that they exist. Could show up on like a worksheet or something. I won't put any of those on a test. So what about zinc and silver? There's this triangle on the periodic table, and this is how I remember it. Here's aluminum. Aluminum is in group 3A. Aluminum has a 3+ charge. And then we need to remember zinc and silver. And I think of going down the stairs. 3, 2, 1. So zinc is +2 and silver is +1. Cadmium, indium, and gallium also fall in here. Cadmium's going to be +2 with zinc, and gallium and indium are going to be +3 because they're in group 3A. But those are unusual elements, so we're not going to run into them very much. So the ones you need to remember here are on this slope: aluminum, zinc, and silver. So if a metal is in group 1A, 2A, 3A, zinc or silver, no Roman numeral. If it is not, then it needs a Roman numeral. So that was the cations. What about the anions? Well, there are monoatomic anions and polyatomic anions. Monoatomic anions are just one atom that has gained some electrons. These are nonmetals, and like women often change their name when they get married, they change the ending of their name, right? Before I got married, my name was Jody Johnson. And that was really easy because everybody could pronounce it and spell it and everything. And then I got married, and now I'm Jody Kawagoe. So I changed the ending of my name, right? When the nonmetals become part of a compound, then they change the ending of their name. And they change the ending to "ide." So fluorine, when she gets involved, becomes fluoride. And bromine becomes bromide. So we change the ending of the name. So binary ionic compounds, this is where you have a metal cation and a monatomic anion. Binary means two. So there's two elements only. And these are the simplest, so we're starting with those. So you just have the name of the cation plus the name of the anion with a space in between. So you name the metal ion, you name the nonmetal ion, and you're done. So here are two examples. KCl. We've got potassium. We find potassium on the periodic table. It's in group 1. Doesn't need a Roman numeral. So his name is just potassium. So we write potassium. And then we have Cl. Cl is the nonmetal. Change the ending of chlorine to chloride. And so this is potassium chloride. CaO. We look at the first element. It's calcium. Find it on the periodic table. You ask yourself, is it in group 1A, 2A, 3A, zinc, or silver? Yes. Doesn't need a Roman numeral. Calcium. And then oxygen changes the ending of her name to "ide." So we have calcium oxide. Naming compounds and writing formulas is something that a lot of students struggle with. It is important. It requires practice. It's like learning to play a new card game. I'm explaining the rules to you, and they may or may not make some sense. You won't really know if they made any sense until you start playing. You need to play with people who understand and say, nope, that's right, not right, you can't do that. You can only put down one card. And so you're going to practice, and Mastering Chemistry will say, no, that's not right, try again. Or we'll do a worksheet in class, and I'll say, no, that's not quite right, try again. And that's how you learn. Once you persist through it and get it, it isn't hard. But you have to persist through and practice. Let's do a couple of examples. Let's name this compound. The formula is Ag3. The first thing we do is we look at the first element. It's silver. That's a metal. This is an ionic compound. And so we find silver on the periodic table and ask ourselves, is it in group 1A, 2A, 3A, zinc, or silver? Well, duh, it's silver, right? So it does not need a Roman numeral. So the name of Ag is silver. So that's the first name. The second name comes from the second element, nitrogen. Nitrogen changes the ending of her name. Nitride.
What's the difference between nitrate and nitrite?
Between what?
Nitrate, nitrite, and nitrite.
Oh, that's a good question. What's the difference between nitride, bless you, nitrate, and nitrite? These are all anions containing nitrogen. The IDE tells me that it's just nitrogen. The ATE tells me it's got oxygen in it. It's an oxyanion. And these you just have to memorize. Nitrate is NO3 minus, and nitrite is NO2 minus. And we will talk about those. Any other questions? So this is silver nitride. There are times when spelling is very important. The difference between silver nitride and silver nitrite, one letter. There are times when one letter difference like that, say on a prescription, could kill somebody, right? It's important. Just like with an email. You type one letter wrong in an email address, and it's not going to get to the person that you intend it to go to. So sometimes details are important. Yes?
When So as far as spelling goes, I'm pretty bad at spelling. So besides the ending, the critical part, let's say I put like on a test or something, I put FO for fluoride, I put FO fluoride.
Right. So he says he's bad at spelling, and he's wondering, you know, how far basically can you go and be okay. You need to do the best that you can. For testing, it will be multiple choice, and so you'll have to pick out the correct spelling. There will be, like on the memorization quiz, there were a couple of spelling foils, is what we call them, where the word was just spelled wrong. But for the most part, the endings are the really important part. You know, if you put two T's here, I would know what you meant. If you change this D to a T, I have to assume that you meant what you wrote, and that's wrong. Let's write this formula. So this is doing it the other way around, writing the formula for rubidium sulfide. So there are two names in this ionic compound's name, and there are two ions. Rubidium is the name of the first ion, and sulfide is the name of the second ion. So rubidium is Rb, and find it on the periodic table. What group is it in? It's in group 1. So the charge is +1. So I'm going to write plus. Writing the formula, you have to look at the charges. Sulfide comes from sulfur. And what does the charge on sulfur? 2 minus. Now that we have the charges, we can do the crisscross thing or look it up and see that it should be Rb2s. Because ionic compounds have to be neutral. The total positive charge has to equal the total negative charge. Any questions? What about the metals that are not in groups 1A, 2A, 3A, zinc, or silver? I'm saying that over and over again on purpose. Then you need to indicate the charge with Roman numerals in parentheses. Sometimes you may look at it and you're like, but I don't know what the charge is. Well, in the compound, you're going to have to look at the charges on the nonmetal, and we'll have to figure it out. So here's an example. Name this compound, CrBr3. Well, we need to write the element symbols and then put charges on them. So we've got Cr, and is Cr in groups 1A, 2A, 3A, zinc, or silver? No, it's a transition metal. This needs a Roman numeral. So when I'm naming it down here, it's like, okay, well, Cr is chromium, but it's not groups 1A, 2A, 3A, zinc, or silver. It needs a Roman numeral. Can I just tell, is it on there somewhere? It's kind of hiding, and I'll show you how to find it.
Can you find it using the balance?
Yeah, we're going to find it using the charge on the other one and the balance, but it's not going to necessarily jump out at you. So what you should do then is put parentheses and leave space to put the Roman numeral in, and then go ahead and finish the rest of the name. Bromine is what? Bromide. So it's chromium something bromide. So I've got Cr and I have Br. Do I know the charge on bromide? Yeah, it's -1. Now I have to figure out the charge on the chromium. The charge on the chromium plus the charge on these 3 bromides must add up to 0. The positive charge has to equal the negative charge. And so some of you can look at that and say, oh, well, it's +3. And some of you can't see that, and that's fine. There are 3 bromines. So here I've got 1 bromine. I'm going to draw 2 more. So I've got 3 of them. What's the total negative charge then? -3, right? And the formula tells me there's only 1 chromium. So the chromium has to be +3. I didn't plan my space very well. So total positive charge is +3. There's only one atom. It must be +3. And so I'm going to put the Roman numeral 3 in the parentheses. Any questions? Figuring these numbers out intimidates some students, and I understand that. The math, though, is really easy. If I said that 3 moms came and each brought 1 cookie, and that there was 1 little boy, how many cookies does he get? You could figure that out very easily because it makes sense to you. And so we can figure the charges out. It's just going to take a little bit of practice. So let's name this compound FeS. Well, what's the name of the element Fe? Iron. Oops. Is iron in groups 1A, 2A, 3A zinc or silver? No, it's not. Therefore, it needs what? A Roman numeral. So I'm going to put parentheses. I don't know what it is yet. And then S is what? Sulfur. Change the ending. Sulfide. I need to look at the charges to figure out what the charge on the iron is. So I have 1 iron and I have 1 sulfur. What's the charge on sulfur? 2 minus. There's 1 of each of them. So the iron must be 2 plus because it has to add up to 0. So this is iron 2 sulfide. Any questions? Let's write the formula for ruthenium-4 oxide. If you're rusty on your Roman numerals, ask me during lab and I'll give you a quick lesson. This is 1 before 5, so it's 4. Well, what's the symbol for ruthenium? Ru. Are you what? Are you tired? No. Ru, sorry. What's the charge on the ion? 4 plus. So the Roman numeral tells us the charge. Common mistake is that people think this should be the subscript. That's the charge on the ion. So this is Ru 4 plus. And then oxide is oxygen, and what charge does that have? 2 minus. So what's the formula going to be? RuO2. Could you make a compound out of that? Ruthenium, oxygen, and potassium? Are you okay? There's a whole bunch of jokes. You know what that one is? That's what the Lone Ranger said to his horse. Hi-O silver. The formula is going to be RuO2. If we do the crisscross thing, we're going to end up with Ru2O4. And then we need to recognize that that's not the lowest ratio. We need to simplify. And it's RuO2. Any questions?
So why is not dioxide instead of oxide? Because
Why is the name oxide instead of dioxide?
yeah, because it has 2 oxygens, dioxide.
That's a good question. Why isn't it ruthenium dioxide? Because that is not the set of rules that we use for ionic compounds. We don't need to specify with di that there's 2 oxygens. We know there's 2 oxygens based on the charges. And so these names, I make up a lot of reasons for things because I need reasons. So perhaps these reasons are not correct, but they make sense to me, so I'll tell them to you. The way I think of this is we want these names to be as simple as possible. We don't want to have to write a whole bunch of extra information. And so putting di in here to say 2 oxides, 2 oxygens, isn't necessary because of the charges. We're going to use prefixes like that for molecular compounds where we don't have the charges to tell us what we're doing. But we're not going to do that with ionic compounds.
So if the charges match, you need the di in front of it?
No, we're not going to use prefixes like di in ionic compounds.
It would be like redundant.
It is redundant, yeah. It's redundant. Now, we may understand what you mean, but that's, like children with baby talk, right? When my second son was about 2 years old, we were at a restaurant, and he kept pointing over to the waitress station and talking about the dollar biller. And we finally realized he was talking about the cash register. He didn't know what it was called, so he called it the dollar biller, right? We knew what he meant, but it sounds silly. So we don't want to make up our own baby talk versions of the chemical names. So we're going to go for correct names. Any other questions? What about ionic compounds with polyatomic ions? We're going to name them the same way. You name the metal, and then you name the polyatomic ion. You have to memorize these. Most of you have gotten them down pretty well. You passed your memorization quiz. Keep those flashcards, though, and keep looking at them, because we need to remember them all the way through the final exam, okay? So this compound here, NaNO2. NaNO2. So it's important to remember there's 2 ions. Sometimes students want to be creative and they want to call this sodium nitrogen dioxide and spread it into multiple pieces. 2 pieces, 2. One's positive, one's negative. So for NaNO2, black's not the best here. There's the metal, that's going to be the cation. Everything else together is the polyatomic anion. If you don't remember what it is, take a stab at it, make your best guess, and then check yourself on that yellow card that I gave you. So this is the sodium ion. It doesn't need a Roman numeral because it's in group 1. And this NO2 is nitrite. So the name of this is sodium nitrite. Here are some of the common polyatomic ions. These guys should be familiar. Hydrogen sulfite is sometimes called bisulfite. That's an older term, and I'm not going to use it. It could show up in a lab or something, but I won't use that on an exam. Bicarbonate, the same thing, and bisulfate. Bisulfite, bisulfate. That just indicates that there's a hydrogen. But the preferred name is hydrogen sulfate. Hydrogen sulfate is sulfate that has a hydrogen ion added onto it. And so it's got the H here, and the charge differs by 1. So there's some patterns in here, and if you recognize the patterns, they can make it easier to remember some of these. Let's look at these 3 here. Phosphate, hydrogen phosphate, and dihydrogen phosphate. This is one of the few situations where you'll see the prefix di in an ionic compound. Phosphate is PO4 3-. Hydrogen phosphate has an H+ ion tucked in there with it, and so the charge goes down. And then dihydrogen has 2 hydrogens. Most of the polyatomic ions are oxyanions, and that means that they have oxygen in them. there is a definite pattern in the names of these oxyanions. So there's, like for this NO2 minus and NO3 minus and NO2 minus. The only difference between these is the number of oxygens. The number of nitrogens, the number of charges is the same. And so 8 is used for the one that has more oxygens, and 8 is used for the one that has less. And you see that pattern here with sulfate and sulfite. If there's more than 2 ions in the series, then we use a prefix. And so the prefix per means more, and the prefix hypo means less. So ClO3 minus is chlorate. 1 more oxygen is perchlorate. This is chlorite. 1 less is hypochlorite. And the same thing, same pattern happens with bromine. Bromine, chlorine, and iodine are all in the same family in the periodic table. They're like sisters. They do similar things. They like similar clothes. Maybe they're fighting over the same guy. But they do things similarly. And if we notice here, the pattern with bromine and oxygen is the same as the pattern with chlorine and oxygen. Chlorate has 3 oxygens and a -1 charge. Bromate, 3 oxygens and a -1 charge. Guess what iodate is? It's the same thing, but with I. So IO3 minus is iodate. And you won't see the bromate and the iodate ones on the table. They're the same as chlorine. So this is how I like to think about these guys. You memorize the 8s. So chlorate, memorize that one. You should have done that already. You can figure out the ones above and below based on prefixes and suffixes. And this is upside down of how it's shown in the text, because it makes more sense to me this way. So perchlorate, per is like part of the word hyper. A hyperactive child has extra activity, right? Extra energy is more. So per has 1 more oxygen than the regular one. Ite is the light version. Bud Light has 1/3 fewer calories than regular Bud, right? Chlorite has 1/3 fewer oxygens than regular chlorate. It's the light version. And then hypo is 1 less than the light version. Where does a hypodermic needle go? Below your skin. Your skin is your dermis. Hypodermic means below the skin. Okay? So that can help you remember some of these. If you memorize the 8s, chlorate, nitrate, phosphate, sulfate, carbonate, you can figure the others out based on the pattern. Okay? 8 does not mean 3 oxygens and a -1 charge. My husband sees a pattern with those, and that's fine. It doesn't make any sense to me, so I'm not going to share it to you with you because I have a hard time.
One difference of 1, doesn't it?
The 8s and the ites are always a difference of 1. You see, phosphate has 4 oxygens and a -3 charge. Sulfate has 4 oxygens and a -2 charge. So you really just need to memorize sulfate, phosphate, chlorate, carbonate, nitrate, and then you can figure the others out. Okay? So let's name compounds and write formulas. So here, this is this guy. Now what's up with the parentheses in there? We didn't talk about parentheses. This is a polyatomic ion on the inside, right? When we have more than one of a polyatomic ion, we put parentheses around it because otherwise it gets confusing. So if I wrote this without the parentheses, assuming that I could make that legible. That could easily be mistaken for one tin, 1 chlorine, and 32 oxygens. But that's not at all what I meant, right? So what we do is we put parentheses around the polyatomic ion. It's like a bundle pack at Costco. It's literally got shrink wrap on it, right? The parentheses are like the shrink wrap. You can have 1 chlorate, you can have 2 chlorate, but they won't let you buy 1.5. You know, you go to Costco and the 2 bottles of ketchup are shrink wrapped together. And you say, but I only want 1 bottle of ketchup. You say, sorry. If you can't afford both of them, you'll just have to go to another store. We can't break it up. We're not going to do that. Polyatomic ions are like that. You can't just break them up. And so we put parentheses around them if there's more than 1. If there's only 1, it's okay. There's not going to be any confusion. Okay, so that was the parentheses. So let's look at this. We look at the first element, tin. Tin is a metal. This is ionic. So far, all of these are going to be ionic because I haven't talked about anything else yet. So tin. So I'm going to write its name. And then I'm going to ask myself, group 1A, 2A, 3A, zinc or silver? Not in that groups, right? It needs a Roman numeral. We're not going to worry about what the Roman numeral is yet, but I'm going to put the parentheses there so I don't forget to write it down later. Then I'm going to ask myself, what's the name of the thing inside the parentheses? Chlorate. You memorize it. Okay, how do I figure out the charge on the tin? I need the charge on the chlorate. So I have chlorate has a -1 charge. And I've got tin. This 2 is telling me I have 2 of those chlorates. So what's the charge on the tin? 2+. So this is tin 2+, so I need the Roman numeral 2. The Roman numeral is the charge on the metal ion. It is not how many there are. Okay? Any questions? Write the formula for cobalt-2 phosphate. I'm going to write each of the ions with their charges and then figure out how many I need. So the symbol for cobalt is CO. Try to make that definitely a lowercase o, because CO and C capital O are very different. This is a metal, and that's carbon monoxide. CO, what's the charge on it? 2+. I don't need the periodic table. The Roman numeral tells me the charge. How easy is that? Phosphate. PO4, 3-. When you're doing homework, try to do those formulas without looking it up. But then after you write down your guess, go check. That'll avoid unnecessary mistakes in your homework. So what do I do here? Yeah, so the lowest common multiple is 6, so I need to multiply the 2 by 3 and the 3 by 2, or crisscross. So cobalt 3, PO4, there's going to be 2 of them. So I need to put parentheses so it doesn't get confusing. And that's the formula for cobalt-2 phosphate. Any questions? Yes?
How would we figure out, say we don't have a sheet to tell us the charge of phosphate?
What if you didn't have a piece of paper chart that told you the charge on phosphate? You'd have to guess and hope that you're right. That's why you have to memorize those. So that you don't need the piece of paper, it's going to be in your head.
So we can't figure it out.
The charge on phosphate, you cannot figure out. No, there's no figuring it out. You memorize it. You know it or you don't. Any other questions? hydrated ionic compounds. We're almost done with lecture. Okay, I know you're getting tired. Hydrates are ionic compounds that have water associated with them in their crystal. And what makes this different than just a wet ionic compound is that they have a specific number of water molecules that get incorporated into the crystal structure. So Epsom salts, you might have heard of that. If you've got a sprained ankle, you might soak it in Epsom salts to help take down the swelling. This has the formula MgSO4, so that would be magnesium sulfate. And then there's this dot, which does not mean multiplication. Dot 7H2O. This is telling me that for every MgSO4 unit, there are 7 water molecules associated with it. When it crystallizes, it incorporates 7 water molecules into its crystal structure for every formula unit of magnesium sulfate. The systematic name for this is going to be magnesium sulfate heptahydrate. Hepta is the prefix meaning 7. So here we're going to use prefixes to indicate the number of water molecules. If we needed to find, well, we haven't talked about that. I won't go there. Here's another one, COCl2.6H2O. We would name the ionic compound the same as we've been learning to name ionic compounds. It's going to be cobalt and chloride. Cobalt is not in group 1A, 2A, 3A, zinc, or silver. It needs a Roman numeral. Based on the charge of the chloride, we figure out that the cobalt has a 2+ charge. Cobalt 2 chloride, and then hexa is the prefix for 6. Hexahydrate.
Why is it sulfate, not sulfide?
Why is it sulfate and not sulfide? That's a good question. Sulfate is the name of the polyatomic ion. Sulfide would just be sulfur by itself. If it ends in ate or ite with a T, it's an oxyanion. And if it ends in ide, there's no oxygen. Sulfide is S2-. Sulfate is SO4, 2-. Sulfite is SO3, 2-. Okay, any other questions? Yes?
So that dot thing, is that purely used for denoting hydrates?
Yes. The dot is used to tell us it's a hydrate. The cobalt chloride and those 6 waters are together in the formula.
But it's only for hydrates, it's not for any other type of combination of 2 separate molecules?
I am not aware of any other type of usage of that dot in chemical formulas. Here are the prefixes that are used. You need to know the meanings and the names of these prefixes. A lot of them you might recognize from geometry. Tri, how many sides does a triangle have? 3. How many sides does a pentagon have? 5. Hexagon has 6 sides. An octagon has 8 sides. Hepta is a little bit weird. Sorry. Tetra. Tetris. In the game Tetris, it's always 4 things, 4 little squares in a different things. These do come from the Greek words. Yes, these are derived from the Greek. The hemi might come up once in a while. Hemi means half. Like a hemisphere is half of a sphere. The northern hemisphere is the northern half of the globe. Hemisphere. Yeah. The cool thing about prefixes and suffixes, they show up in all kinds of different places and they generally mean the same thing. And so you can see this really weird word and you're like, oh, well, I know what this piece means and I know what that piece means, and it can help you figure out what the word means. So let's name these hydrates. What would this one be?
Calcium sulfate hemhydrate.
Calcium sulfate hemihydrate. So calcium, and we find calcium on the periodic table. It does not need a Roman numeral. Sulfate, and the prefix for half is hemihydrate. Yeah, how does that work? How can you have half a water molecule? Well, that means that there's one water molecule for two of these formula units. But we always write this in the lowest ratio. And so it comes out being weird like that. How about this one? Barium chloride. This barium doesn't need a Roman numeral. And hexahydrate. We will use these prefixes for other things besides just hydrates. Yes, question?
For the iodine changing name, does that apply to all of the elements or just a seven?
For the
Or sorry, changing the ending to I.
changing the ending to "ide" works for all the nonmetals. All the nonmetals. The metals are either just the same name as the element for their ions or the name with a Roman numeral. And you see that trend among male humans as well, right? It might be John Smith the Fourth, right? You don't often see Mary Smith the Fourth because of our tradition of taking the husband's name. That name doesn't get passed down. And it's just how it is. Yes?
So if you had like iron and nickel, it would just be iron nickel?
Iron and nickel won't form a compound.
Well, that's just, are all the transition metals like that, where they don't form compounds with one another?
Metals do not form compounds with each other. They will form homogeneous mixtures, and we call those alloys.
Right.
So things like brass and pewter are homogeneous mixtures of metals, but they are not compounds. Yeah. Metals do not form covalent bonds. And they also don't form anions. So you can't get positive ions to stick to each other, and the neutral atoms won't stick to each other either. So yeah, metals and metals do not form compounds. Any other questions? Okay, let's write this formula. Copper 2 sulfate. When you're first starting out, I really, 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 really want you to write the symbol with the charge. So we need to write Cu, and what's the charge on it? 2 plus. And sulfate is what? SO4 2 minus. We look at that, charges are the same, we can just put them together, CuSO4. After you get good at it, like really good at it, then you can skip this part. But just starting out, write it down. And then hexahydrate. A dot and 6 H2O. Any questions?
You would have put parentheses H2O then 6.
I would not put parentheses H2O and then 6. There are compounds where that notation is used, but those are not hydrates. They are complex ions, and that's covered in a different class. Good question.